Okay, so here, you guys, please use thinking strategies, which is what these are called. Adding things to find 10, all that kind of stuff, they're called thinking strategies, which I really love. What thinking strategy could you use for, why? Sorry, there they are. 9 plus 8. Don't say anything, just take a second. I know you know what 9 plus 8 is. Use a specific thinking strategy. I love you. Somebody should walk in and go, excuse me, 9 plus 8. What class is this? So I'm going to show a couple actually. I know there's one that probably everybody's doing. What is somebody doing? What strategy are you using? Anybody? Nothing? You guys are all drawing anime? Yes?
You could subtract 1 from 8, so then it'd be like 9 plus 10, so you'd round.
So like 9 plus, how would you rewrite 8?
8 plus 1, or 7 plus 1.
7 plus 1. I like it. And then you can use associativity, commutativity. All right, I like it, right? Okay. And again, what we're discussing right now is what your students will be doing as they're learning this stuff. We all knew the answer was 17, hopefully we all did. But just the way a student would get to it who's not used to using this. What about, are you doing all right? Yeah. Okay. Here's a nice quick, oh yeah, so I was going to do a different way. Here's a different one. What about 1 plus 8 plus 8? And isn't this the doubling? Right. So that'd be 1 plus 16, because they can think 8 plus 8 is just double 8, 16, and they get 17. Woohoo! Whee! Okay. What about, what else you got, Jeff? Oh, this one's not too bad. This one's too easy. Let's see. 42 plus 7 plus 18. This one we already did, basically. All right. So what are you guys doing to make this? To do this as easy as you can, right? And I want somebody to go, I thought about using a calculator, so I did. So that was my strategy. Yes?
Like like binary would be like doing the 42 and the 18 together.
Yeah!
You know,
And of course, what are you actually using? What property?
commutative.
Yes, good.
Yeah.
So you can switch the 18 and the 7. 42 and 18 is 60.
67.
Yeah.
Or another way, if they're like 42, that number is huge.
Huh?
They would bring it down to
Yeah, I like it. So,
20.
oh, okay. I thought you were going to
Two
do
20s, and then do the 2 for the 18.
So here's a different thing. This is what I thought you were going to say. 42 is 40 plus 2.
Right.
I did that.
Oh, you did this? Cool.
Okay.
And then you got 2 and 8. It's 10. And then 10 and 10 is 20. And then you got 67. Yay.
Yeah.
And all right. This kind of thing, some parent sees it and they flip the shit out because they're like, why don't you just do 42 plus 18 carries? Because that's what you would do next. This is actually known as an algorithm that kind of uses the ideas, but you can't use ideas until you understand the freaking ideas, right? So that's one thing I like about Common Core is it does start to build ideas instead of just making them memorize algorithms. So when they get to this, they're like, why does this make sense? What does it relate to from what we did before, right?
And a lot of it like becomes, or it's supposed to like become like shortcuts.
Yeah.
There's, I don't remember what it's called. Kumon.
Oh, Kumon. It's funny. You're the second person it is said something about Kumon.
Because, I mean, we used to not have it like in the curriculum in school, but they had like exercises, and it'd be like, yeah, this is stupid. And it's like 4 times 5, like 80 times, you know. But it's that idea of like commutativity.
Yeah.
Now I'm thinking back, and I'm like, I guess it wasn't that stupid. Yeah.
But I mean, yeah, nowadays we're starting to move in the direction of less memorization, which I'm okay with to a point, but you have to memorize enough to have something to work with, right?
Yeah.
So students are coming into college, for example, this is kind of a weird example, but do you know what the word of means in mathematics? So if I said, what's 25% of 80? Nope. So let's say there's 4 apples in a crate, and I have 3 of those crates. 3 of crates that have 4 apples. 3 times 4 of means times. So 25% of 80 would be 0.25 times 80. And this is not your fault. Everybody used to know what of meant. And over the years, fewer and fewer people did. And I'm like, what's happening? And they're just not teaching that. Anyway, that's a bad example of memorization, but still, that's one thing that's I've noticed. Those are all kind of the same. Let me see.
Is there such a thing as like a mathematical language class, or is it all just in the classes?
Well, basically, any math class you take, you're taking a math language class, right? And I've basically said that really directly before about translating from English to Mathish, right? That's really what it is. And it's hard to learn. So for example, it would be really weird to take an entire class devoted to just single words and how you say that in Spanish or something, right? Wouldn't you want that class to not just do that, but to also show how they go together in a sentence, what the grammar's like? So that's what math is. Math, the words are the symbols. The operations and the order they work in is the grammar, right? So it's very similar, yeah. Do they have any more interesting?
Ain't, and then there's some people saying ain't as if it's like a
Oh yeah.
word, and then there's some people doing some math.
It's crazy. Okay, I think the other things are kind of silly. Most of them are based on that one strategy, which is weird. They got the doubling strategy, you got the finding 10 strategy, and then of course you have associativity, commutativity, that kind of stuff. I like it. Let me see if you guys remember this. What do you got, Chef? Write it down. There it is. 5 base 6 plus 3 base 6. See, now you guys are not stuck in, I know this stuff, because you don't know this stuff. Now you got to really think about the strategies themselves, which is one reason why we do this to you, so that you know what your students are going through with base 10. This is related to a strategy we just used, and we used it earlier too. I just want to see if you guys remember. What can I do?
You take one off to make
Take one down, pass that around. So 5 base 6. So I can break up the 3 as 1 base 6 and 2 base 6. Because what's 5 base 6 plus 1 base 6? 1 0 base 6. Or 10 base, plus 2 base 6 is 12 base 6. I like that. Now obviously, what's 5 plus 3? Just 5 plus 3. 8. What's 12 base 6? That's 2 1s and 1 6. What's 2 1s and 1 6? 8, right? So we're trying to get away from that, because you could just do this and then convert it. We're trying to live within the system so we can get used to the strategies. So if you see a problem with this, don't do that. Don't translate and then translate. You're kind of going around the strategies, which I guess in itself is a strategy, but it's one I'm not allowing you to do. Ha ha. Okay, now we get some really nifty stuff. So that's addition. So remark right up. You didn't know this was coming. We're gonna do subtraction now. Subtraction gets kind of nifty with, well, just generally, but with the set method, it definitely gets nifty. Is this what they do? Not yet. Okay, later. That's right. That's right. When we get to negative stuff, it's going to get exceptionally nifty. So it's just a little nifty right now. If I wanted to do 5 minus 3, but I want to use the set model, how could you set up something that would represent 5 minus 3? And of course, what do young people, what do you normally call subtraction? There's a 2-word phrase. When I subtract, like give me a physical example of 5 minus 3.
Less than?
Take away.
Mark has 5 marbles. Keep going. Jack takes 3 away. How many does Mark have left? Right? Is that what his name was? I forgot what was that, like less than 10 seconds. I forgot his freaking name. So Mark's losing his marbles, which you can all relate to. So that would be a takeaway, right? Takeaway. That's another name we use for subtraction problem. We call it a takeaway problem. So here's what's kind of nifty. I'll get even niftier when we get to negative numbers, because I know some of us have definite residual problems with fractions. Would you agree with me? Anybody have some issues with fractions? Some of us actually do still have residual problems with negatives, especially when you're trying to combine a bunch of shit. That some's negative, some's positive. And then when you multiply, it's different rules, right? Okay, maybe not so much. Okay. So here, if I have 5 things, and I'm just going to make them all. They're 5 distinct triangles. What do you hope you could do to model this? Just directly.
Scratch 3 off.
Okay, you could scratch 3 off, but then you would lose what the original problem was. So an alternate thing, we're not going to draw a hand coming in, but we could just do this. So that model's taking 3 of them away, and then you can see exactly how many's left, right? And of course, this drawing is something you can actually have on the table.
Yeah.
Yes? And they can move stuff around, which is what they want to do. I don't blame them. It's neat moving shit around. So this would represent, this looks like a really tortured pumpkin, but this would be 5 minus 3 leaves you with 2. It's crazy. It's crazy. You're all like, thank you, Jeff. I didn't see what was happening. Okay. So that's kind of nice. That also illustrates why they can't understand this yet. Right? And this also illustrates why people throughout history thought this was bullshit. They looked at it and they thought, that's bullshit. Right? Now we're cool with this, right? What is 5 minus 6? We're cool with that. How about if I say, let me push this just a little bit. What if I say, like, you guys know what the square root is, right? What's the square root of 9? 3. Everybody's cool?
Yeah.
What's the square root of negative 9? Does anyone know? Square root of negative 9?
3.
3 times 3 is not negative 9? Negative 3 times negative 3 is 9? Oh shit, so what's the square root of negative 9? Can't do it. It's what's called imaginary. That's what an imaginary number is. The word imaginary is unfortunate. I was going to say another word. The word imaginary is unfortunate because they're not, they actually exist. They do. So later this semester I'm going to show, I think I'll show you that one video later. That's all I'm going to say about imaginary numbers today, okay? But just like they thought 5 minus 6 was bullshit, and now we know better, square roots of negative numbers are also not bullshit. But unfortunately the imaginary name stuck on. 5 minus 6, if you try to show this to a young student, you got 5 things on the table, and you're like, take 6 of them away. They're more than likely going to start, and then they're going to look at you like, I can't do it. They can't do it, man. What the shit? Okay. So that we're talking about later, of course. But you see how this is a really, I mean, for humans before we evolve very far with our mathematics, and for little people before they grow up very much, this is, Alright. Now, of course, let's see if they get any more interesting. Not really, okay. We also have the other, what's the other model that we've used so far? We got the set model, measurement model, kick ass. That's sort of interesting. Okay. So if I wanted to do 5 minus 3 on a number line, how would you do that? Start at 5. So there I am, standing there. I got a really long neck. And then? Yeah. So it's kind of a separate thing than the takeaway. Again, this is motion. So you get the adding is going right, subtracting is going left, and what's really cool for the student is if you did this problem and then you gave them this problem and then they see it's the same answer, that solidifies there's an idea. I don't see how to say it. There's an idea that covers both of these ways of looking at it, right? Because they get the same answer. 1, 2, 3. And then they get 2, 3. So in the homework, they're going to say stuff like, illustrate this with a set model. Okay, you got to know what the set model means. You got to know how to set it up. They illustrate this with the measurement model. Blah, 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 blah. Right? Both are pretty simple. You just got to know what each of them means. Oh, before I forget, remember how we had all this stuff about A plus B, and it was the sum, and they were add-ins or sum-ands and all that kind of weird shit. So I already gave this away. That's a difference. Now this is where things get really strange, and I'm gonna cheat because I don't even remember these words. A is called the minuend. Minuend, yes, minuend. Sounds like ballet move to me. I don't know. No, minuend. Okay. And then this one's called. No, this one's even better. This one's called the subtrahend. Write them down or forget about them. I'm never going to ask you about them. All right, they're just there, just so we know. They have names, the little parts of a problem. Okay. Now, the next thing, and this is what I forgot, I did this last time. I didn't really finish my notes this morning because this morning was crazy. So I'm just sort of winging it now. But normally I start with the next one first because the next method for subtraction connects it to addition. And this is what you continuously want to do. When you teach multiplication, then you start to teach division, you make the connection with multiplication because they know, or at least have seen, multiplication. You want to give them a bridge to the next idea. So, another way to look at, let me see, what's a good example? Blah, 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 blah. Okay. So if I want to do 5 minus 2, I can look at it the missing add-in approach. So 5 minus 2, the number that the answer is actually what you add to 2 to get 5, the missing add-in approach. So it's sort of like, it directly relates to a physical problem like this. You have 5 Slim Jims. I must be hungry, I don't know. You have 5 Slim Jims. I have 3 Slim Jims. How many more Slim Jims do you have, right? That kind of thing. And of course, I forgot I said 2 up here. You have 5 Slim Jims. I have 2 Slim Jims. How many more Slim Jims do you have? You have 3, because 2 plus 3 is 5, yes? So that's the missing add-end. So what they're thinking then, when they see 5 minus 2, they're going to think 2 plus what is 5. Mm-hmm. And they've got some of that memorized by now. They've got something to stand on that they work with before. Okay, I like it. I like it. Excuse me. The set model for this kind of is interesting. So I know how much I'm taking away. I'm taking away two things. So what must have been here so that I would have started with 5? So I'm taking away two things. Again, this is the same idea, correct? It's the missing add-in, just what does it look like in set model? So they'd have to think to themselves, there must have been 3 out here, so there would have been 5 altogether. Okay. Blah, 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 blah. Okay, let's get more into it. Okay. Let me see how I want to put this together. This next thing is a little bit interesting. Let's see. All right, so we got this here. It looks like an alien bowling ball. Okay. This picture is, let me see, there's a picture on page 95, if you have your book, it's at the bottom of the page. It's a little bit strange. I like all right, let me do this. Let's try to build our way up to this weird picture. What time we got, okay. Go home, camera, you drunk. Okay. Stay. Do nothing. Alright, so this up here hopefully makes sense. There it is. So they kind of give us a little matrix. Watch out, matrix. The set model takeaway. So let's see. Ashlyn had $7 and spends $3 on candy. So somebody physically took $3 away from her and gave her some candy, right? Okay. So that's the takeaway approach. Missing add-in. McKenna has $3 but needs 7. So you see how that physically directly relates to the missing. It's actually missing money. So it physically directly relates to the missing add-in idea. Could you use missing add-in on this? Sure, you could set it up. But this one physically directly relates to it. The set model is because this is like, these are physical things, dollars and candy, whereas this one is about distance, which is what I was talking about. The measurement model kind of goes with distance really well. So Christine ran 7 miles from home and then ran 3 miles back. How much farther does she need? So she took away 3 of the distance that she got away from the house. And the missing add-in, Shauna has run 3, wants to run 7, so how much is missing? But aren't both of these the same answer?
Yes.
But they physically represent different ideas between the two, yes? But the work is the same, okay. Now, here's where things get pretty. Where are they? Here we go. Look at number 2, I think. Here we go. I think. Hold on. Actually, both of these. Monica was 59 inches tall last year. She had a growth spurt and is now 66 inches tall. How much did she grow during this past year? Yeah, so that kind of fits into the problem. They tell you which thing they would use. I mean, can you see how this is missing added? Because we know where she started, we know it's just missing how much she added. Okay, that's pretty straightforward. Monica joined a basketball team this year. One of her teammates is 70 inches tall. How much taller is that teammate than Monica? So did Monica lose something or gain something? Did anything happen to Monica? No. This is still a subtraction problem, yes? But this is sort of a new dimension to this thing, right? And I kind of chose that word on purpose. So this is a comparison, which makes sense, because you're comparing her to somebody else. So if I add a dimension to this, we should know this from our little manipulatives that I thought we would get to, but I don't know if we will. Actually, I kind of passed the point I could have done that. Oh, well, it's just the way today. If I add another dimension to this, what shape is it going to become? What comes after a flat?
Cube.
A cube, all right. Right, which is down there. That looks exciting. So the front face of it is what's up there, right? The matrix. But then you could also have, is it a comparison problem? No or yes. And then you can apply any of these. And then that just makes the whole thing, to me, I wanted to talk about this because it's in the book. If you look at it, it just makes it a little more complicated than it necessarily has to be. It almost doesn't matter if it's a comparison problem, yes or no. What matters is what method do you need to or should you use that goes more directly with the physical nature of the problem. Okay, maybe. Because what's really important is they're going to attack a problem for which they do the same work. But again, every single one of those had the same work, I mean, some of them, but the way you set it up was a little different physically, right? So it's all about, you want the idea of 7 minus 3 to mean something, but to do that, you got to show, here's a situation that leads to 7 minus 3. Here's another one that's a different thing that you can think about that also leads to 7 minus 3. I don't know if you guys are really with me, but it's really hammering home that 7 minus 3, it's its own thing, and it applies to these different situations, but when you're learning, you want to start with a situation and go backwards, because situations, you can mess with stuff, you can give one kid this many things and the other kid this many things, you can physically do stuff. Then you tie it back to 7 minus 4 by itself means something, without any physical stuff attached to it, but you can't start there. Okay. Blah, blah, blah. Oh! Anything else here? Not really. Well, I mean, let's see. Blah, 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 blah. Yeah, so, okay. Here's a little tiny thing about comparison approach. If Larry has $7, oh, you guys can't see shit. Larry has $7 and Judy has 3. How much more money does Larry have? So over here, here's Judy's money, here's Larry's money. So you find the set of Judy's money in Larry's money, and then you can see the excess Larry has. This is same stupid, it's still subtraction, yes? I really want you guys to see it. I don't mean to use the word stupid, you know, it's kind of silly on one level, it's all the same word, but physically, very different setup.
Yeah.
Okay. And there's a really bad drawing of that's supposed to be Ben Franklin. It's fun. I can't speak though. I would draw it worse than that. Okay. This is cool. Okay. I want to make sure I didn't miss anything. No. Okay. The next thing we're going to be doing is multiplication division, which is going to get pretty nifty. We got some approaches that should be very expected, right? One of the most basic ideas of multiplication is like the area of something, right? A quick way to count rows and columns. I love it. When do we finally, I don't think it's off for another while. No, it's not for a while. Oh, geez. Sorry, I just can't wait for negative numbers. But, I'm gonna have to. I think we're a little early, right? We did everything I wanted to. Yeah, we're not that early. We're a little early. Don't get used to it. So why don't we head out? Anybody upset about that? Anybody feel like I'm not giving you your money's worth? I actually had somebody upset one time.
When should we turn in the test corrections?
When?
Yeah.
Any quiz or test corrections due by the day of the next test. Yeah, so as long as it's by the day